Hello everybody. In Lab 2, I observed and analyzed the motion of a bowl of mac and cheese falling straight down due to the force of gravity. Because we do not live in a vacuum, I had to take into account a drag force, or air resistance. The physics at play here revolved around Newton's second law, the velocity and position update formulas, a non-zero net force, and of course the force of gravity and the drag force. Here's my tracker video. My 16 frames of tracker motion gave me my initial conditions, a start time, a final time, my initial position, and then my initial velocity. I tried calculating it at first, but I soon realized that was a bad idea, and the ball starts at rest, thereby initial velocity must be 0. I know that the F-net for my gravity computational model will solely be negative mg in the y direction, and then in the drag model, it will be the force of gravity added to that, the force of drag. This is my code and model for my mac and cheese falling under the force of gravity only. I inserted my initial conditions through here, and then in the while loop I made sure that F-net was equal to the weight force, which is equal to the ball's mass times gravity times j hat times -1. And then in order to update the ball's position and velocity, I used the given formulas, and then I put some arrows on my model so I could see the forces acting on it. And here's the program in action. As you can see, we have our model up top, graph in the middle, and our helpful points down below. Here is the code for my model with gravity and drag. My initial conditions stayed the same as the previous model. However, I made sure to include my drag coefficient, which I found by guessing and checking. And then I made sure my F-net would be my weight force plus the drag force, where the drag force is equal to the magnitude of the ball's velocity squared times my drag coefficient. And I made sure that value was positive so it would counteract gravity. And then my arrow data was exactly the same, and that produces this program. As you can see, it's very much the same, but there's a drag force acting in the upwards direction. Once I got my 3 sets of data, I put them in an Excel spreadsheet and made this graph. As you can see, with the blue and green lines, there is a big difference between the final position. That's because the blue model did not account for drag, it only accounted for gravity. So when I introduced a drag force into my second computational model, I got this yellow line, which correlates much nicer with the green line. As you can see, when I made my velocity time graphs, I kept the colors the same. So the blue line, which was gravity, became perfectly linear, which is expected as velocity is the derivative of position. My drag model became this kind of strange back half of a parabola shape, and it seemed to want to approach this -4 value. So I hypothesized that -4 could be the terminal velocity for my system. And then my observed velocity is really weird. There could be some error in that. I'm not exactly sure what the problem is, but I'm eager to find the solution. When my initial velocity was equal to 0, the terminal velocity appeared to approach -4. I've now gone into my drag model and replaced my initial velocity with 2, and I've changed the graph output. As you can see, with an initial velocity, it appears as if the terminal velocity is approaching -4.5. So, if an object has an initial velocity, it is probably safe to say that its terminal velocity will change. I would like to conclude by stating how surprised I am to see how big an effect air resistance has on an object's motion. In becoming a mechanical engineer, it has been beneficial to learn about the importance of the drag force. Thank you for watching.